Hi everyone, Vega here, and in today's video I thought we'd return to our exoplanet series, and I found this list on Wikipedia of exoplanet extremes which I thought might be quite interesting to go through. It says here the most distant exoplanet discovered is Sweeps 11, and it says approximately 27,710 light years away from the solar system, which of course leaves it within the Milky Way. But certainly a long way away if we think of the centre of the Milky Way being 25,000 light years. It's further away than it would be to get to the Sagittarius A star. It's quite incredible really that we can see something so far away, isn't it? There's the size comparison to Jupiter, so it looks like it's slightly more voluminous than Jupiter. And it's also a hot Jupiter, it says 9.7 times the mass of Jupiter, taking only 1.8 days to go around the host star, although it doesn't say what the host star itself is. The least distance exoplanet, of course, is Proxima Centauri b, or I suppose it could be C, depending on where it is in its orbit. Presumably at the moment it's Proxima b. Proxima b we won't spend too long talking about because I think people know fairly well it's quite a small world, but does orbit close to the habitable zone of Proxima Centauri, although not. As you can see here, it does orbit very close into Proxima, and there is a D and a C planet, although I think they're still disputed. The closest directly visible exoplanet is Epsilon Indi AB, which I think you may have seen this picture before here. Obviously we can see the starlight has been dimmed out, and this presumably here is exoplanet Epsilon Indi AB. The Epsilon Indi system is quite an interesting one. I don't think I've done an individual video on it, but as we can see here, it has a K-dwarf star, which is the A star, and then it's got two presumably brown dwarfs. So you've got an Alpha Centauri B-like star and also two brown dwarfs in orbit around it, probably worth a video on its own at some point. And of course this super Jupiter, it says here a mass of 6.1 Jupiter masses and an elliptical orbit. They're quite curious, aren't they, these elliptical orbits? It does make me question the data. I'm not an expert and I'm sure the data's correct, although it does make me question it just purely because it's so different to our own known solar system, where our planets, although they do have eccentric orbits, they're mostly circular for the most part. The exoplanet with the largest radius is DH Tauri b, and it says here the radius is 2.7 plus or minus 0.8 Jovian radii, which does make it quite enormous, doesn't it really? Obviously with these larger exoplanets, the distinction really between brown dwarfs and planets is being pushed to its limit really. I mean, look at this particular one, DH Tauri b has a mass estimated to between 8 and 50 Jovian masses, which again does push the limit, doesn't it, really, between what we think of as a planet and what we think of really as a failed star or brown dwarf. Quite interesting here, it says it's potentially orbited by a smaller candidate companion, DH Tauri bb, which is possibly an exomoon with 1 Jovian mass. So you've got in the DH Tauri system, you can see here this is presumably the star, and then we have a super Jupiter which has a Jupiter-sized moon, which is quite curious, isn't it? The most dense exoplanet is somewhere called GP Cómo Berenices b, and it says, according to the IAU working definition of exoplanets, being 10 times more massive than Jupiter is a planet, despite that it might have formed as a white dwarf that was stripped down to a planetary mass object. That's very, very strange, isn't it? For reference, it's a lot denser than osmium, the densest naturally occurring stable element on Earth. So if GP Cómo Berenices b is indeed a planet, the material it's made out of is denser than anything that forms naturally on Earth. So a very interesting world, and again curious, because as far as my understanding is, there's not really any mechanism for making an object that is as dense as a white dwarf that only has a planetary mass. Presumably somehow it lost mass and became a planetary sized object, but I don't know the mechanism for that. Perhaps someone does in the comments, let me know. And the least dense here is Kepler 51d, which it says it's a hot Jupiter, so again a planet that orbits close to its star. and it seems to think it's some sort of highly evaporating planet, which does sort of make sense, doesn't it, if it's close into its star. And it's a tiny density. Actually, it says it's a super Neptune planet, so it's not really a hot Jupiter in the sense that it's like Jupiter. It's more a Neptune size of world. So imagine if we took the planet Neptune and pushed it towards the sun. I know there's quite a large content of water on our blue planet, our ninth planet. So you can imagine Neptune boiling away. That presumably is what this planet is a bit like. Kepler 51d. The oldest planet is somewhere called Toy 157b, and it says the currently accepted age of the universe is around 13.8 billion years, which presumably you already know that. And it says here that it's 12.82 billion years old. It says here on the NASA website, a giant planet composed mainly of gas, 1,160 light years, and it orbits a G-type star like our sun. But on the NASA site, it doesn't actually say anything about the age of the planet, which is really what makes it interesting, isn't it? And again, it's another one of these ones that orbits really close in to the star. Don't know what anyone else thinks about these close-in planets, but again, I'm no expert. I'm sure that the data's right, and I'm not for a second criticising or even casting doubt on the data or the reading of the data, but it does seem incredibly strange that in our solar system there's nothing of the sort, and yet in so many other systems we find these planets that are basically right next to their stars, sometimes huge planets too. I just find it mind-blowing and very difficult to comprehend, if believe's not the right word, but certainly comprehend just how different these systems are to our own solar system. It says here longest orbital period is Gliese 900b, and it takes 1.27 million years to orbit its star. That's incredible, isn't it? Which makes you think that it must be so far away. Let's see if we can find out how far Gliese 900b is from its host star. Obviously in the sky, as we see it, it's got quite a large separation there, so which you'd expect, wouldn't you, if it's a long way away. Here we are. It says the estimated distance to the system, it translates to a projected separation of 12,000 astronomical units. The planet itself is, again, it's a planetary mass object, so really at 10.5 times the mass of Jupiter. Is it a planet or is it a brown dwarf? And I don't know about what anyone else thinks. The minute it becomes a brown dwarf, suddenly it doesn't seem as interesting, does it? That it's so far from its host star. I mean, we see binary stars and indeed binary brown dwarf and main sequence stars, for example, that do have separations of much larger than 12,000 astronomical units. It's just a curious fact that we're calling it a planet and it's so far that it sort of blows, at least it certainly blows my mind away. Again, 1.27 million years to take one orbit. That's going to be a long winter, isn't it? On Gliese 900b. I think this is probably going to be a 2 or even 3-part video, so let's have a look at one more, shall we, and then we'll wrap it up for today and perhaps come back to this in a few weeks. The exoplanet around a star with the highest stellar mass is an exoplanet that orbits Beta Centauri, or Hadar, which is certainly an interesting idea, isn't it? I think we've talked about the planets of Hadar before, and it's in orbit around a fascinating system indeed of several B-type stars. And Beta Centauri b, sometimes known as Beta Centauri ABB, which makes things quite complicated, doesn't it? A circumbinary planet, so it's orbiting more than one of the Hadar stars, and is a super Jupiter with a mass of 10.9 times that of Jupiter. And yeah, the formation of such a planet is quite intriguing, isn't it, really? Because you've got these huge stars. I mean, Beta Centauri is some of the brightest stars in our skies and the most massive in our local areas. So you wonder how such a world could create itself within the chaos of such massive stars like Beta Centauri. It says it's believed that giant planets are formed by core accretion, in which a rocky core grows to critical mass, and then obviously the surrounding gas is created around the world, which we've spoke about before, haven't it? But it says it can't explain Beta Centauri ABB because core accretion becomes less efficient at large distances from the star. Massive stars like Beta Centauri A cause the disk to dissipate more quicker. It's probable that the planet formed directly from the circumstellar gas through a mechanism known as gravitational instability, which is quite curious, isn't it? That obviously the Beta Centauri planet, or potentially I should say rather than obviously, is an odd planet and it's not formed in the same way. Do we know planets, or do at least we anticipate planets are formed in our own system? So quite curious there. I think we'll wrap it up there on Beta Centauri. It's a great view there of the Hadar stars, isn't it? In distance with the super Jupiter, the sub-brown dwarf, looking at those bright stars. It must be an incredible viewpoint. Look after yourselves well, as always, and care of your family and your friends. I'll see you on the next one.